Let me write a integral here, or two up here. Integral of x squared dx. Integral square root of 1 plus x squared dx. Because, to say this, those look like nice little integrals. Not too daunting of an integral there, either one of those. We've done some that sort of look like those. However, we haven't done exactly those because, come to find out, you just cannot do those integrals and get your exact integral out of that, because, well, if I had an x, if you think about it, if I had x e to the x squared, we did one of those by parts, that would be u substitution, but just e to the x squared, we haven't done one like that, and matter of fact, we can't do it. It's not going to be, we're not going to be able to do those. It's impossible to get the antiderivative of that. So there's still, even with all the techniques out there, the tables, the u substitution, the integration by parts, trig substitution, even with all of those, there's still some integrals that are impossible to do. Isn't that encouraging? But there are. Okay, there are just some. These are two examples. Impossible integrals. You just can't evaluate them directly using any technique whatsoever. You just can't evaluate those. Okay? Well, that's why approximate integration is important, because there's just sometimes you just have to approximate it. We've done some of that previously. Matter of fact, when we just first started in Calculus 1 talking about integration, that's where we started with, was approximate integration. If you think about it, really, that's what we were doing. We were approximating the integral, because for a definite integral, if we're talking a to b of f of x dx, what does that transfer over to, graphically speaking? It's the area under the curve. And so we're kind of going back to that, approaching it as, if we can't do the evaluation here of this, then we can at least approximate it using various things. So yeah, we mean if this is f of x, a to b, then that's the integral, right? Okay. Well, how did we approximate it before? Using rectangles, right? We use rectangles to approximate the area under the curve. Previously, on this same channel, we approximated using rectangles. That's one form of approximation. All right, now, the thing about that is you have options, right? If I do 3 rectangles, well, what else do I need to know? Am I using right-hand endpoints, left-hand endpoints, midpoints? Because that changes it up, doesn't it? Because the heights of the rectangles change. If I use 3 rectangles right-hand endpoints, then, you just go along 1, 2, 3, do that rectangle right there, then do that rectangle right there. Is this ringing a bell? Vaguely something we did. And then get those heights and those areas. So the area of those 3 rectangles roughly approximates the... now, just to remind us of a couple of things here. Recall a few things. Yeah, we go A to B. What do we call these interim x values? Those were the x sub n's. X sub 1, this is x sub 1. This is x sub 2. B winds up being x sub 3. A is x sub 0. Remember all that? Now, how far apart are those? We called it delta x. And delta x was b minus a over n. All right. So all that still will apply. Okay, and so the point of all this is this definite integral here is approximately then sum of all the rectangles, right? And how did that look? Some of the area of the rectangles. How did that look when we wrote it all out? Well, it was something like the sum, wasn't it, of the f of x sub i's times the delta x, I equals 1 to n, in this case 1 to 3. All right. So this was our approximate integration technique before. Okay. So recall all that. Now, what else we did was we used midpoints. And the only thing that changes if this is if it's right-hand endpoints. What if it's midpoints? Well, then the integral there would be approximately, let's draw the picture here. Using the midpoints, we have the integral from a to b of f of x dx, and we said was approximately then the sum of all the rectangles I equals 1 to n was the f of x sub I bars times delta x. That was our midpoint rule. The x sub I bar is the midpoint, so just some notational remembering back in the day. Some of it's been a while. Right? So we covered those previously. And of course the deal is out of the left endpoint, right endpoint, and midpoint, which one was usually more accurate? Remember? It's midpoint, yeah. Because if I go, here's x1, so if I go to x1 bar to do my height, that goes right here, well, I've got some give and take there. Some of it's outside the area, but some of it's, then you got some, so yeah, if I use midpoints there, you got the give and take, and it kind of balances out. Not exactly, but you know what I mean. So yeah, the midpoint usually turned out to be more accurate, and we'll explore that more with what we're going to do. But what we're going to do today is we're going to talk about two other techniques, two new techniques. We did those, and maybe with a little bit of recollection you can remember how you did those, but we're going to cover two more new types of approximate integration here. That's what we're going to do today. New and improved. The first one, technique of approximation, integration approximation, is the trapezoidal rule. Trapezoidal, if I can spell it. We're going to use trapezoids. Forget rectangles. Well, don't forget them, but we're going to go with trapezoids. Now, here's what a typical trapezoid will look like for us. It's going to be a little thin trapezoid. And the deal is, instead of a rectangle up here at top, we're going to have a little angle to it. And so that's a trapezoid. Remember, trapezoid, to be a trapezoid, it's what, parallel sides? So yeah, we've got a trapezoid here, a vertical one, if you will. We've got a vertical trapezoid right there. Now, let's review here. What about the area of a trapezoid? Area of a trapezoid is 1/2. Well, if you call the parallel sides big B and little b, one way to do it, it's big B plus little b, and then times h. Well, the h is the distance between the parallel sides. Okay? All right, so remember that. A little different orientation than, usually trapezoids, you think this. But ours is turned over, and it actually does have a 90-degree angle in it, but it's still a trapezoid because you got the parallel sides. This is the way ours will look. Okay, so let's say we get a curve here. I'll erase that. Still working on our trapezoidal rule. Okay, so we've got a curve here. Let me make it similar to the one I've got on my paper here. So I'm going to go A to B, looking at the integral from A to B. So this function is f of x. Y equals f of x, okay? All right, well, let's look at doing this with 3 trapezoids. So again, I'm going to split this up into 3, right? x1, x2, x3. B is going to be x3, of course. A is x sub 0. We'll use those here in a minute. Okay? So the deal is, what I'm going to do is this. I'm going to come up here to my function, and then, but instead of going with just one height there, I'm just going to go up to the curve here, go with curve here, and then cut that off, and that's going to be my trapezoid. See that? This is going to be trapezoid number 1. So you see the difference. The heights of my function, that's going to be where the cutoff is for my trapezoid, where big B and little b cut off there. All right? So what about the second trapezoid? What does it look like? Well, the second trapezoid comes here and cuts across there. And then the third trapezoid comes up here at x3, and it's a little harder to see that one, but it does cut across kind of like that. Okay, so that's my 3 trapezoids. Now, what are the parts of my trapezoid? Let's look at trapezoid number 1. Trapezoid 1. What is the area of trapezoid 1 there? Well, it's 1/2 big B plus little b times h. Well, what is that in context of my function here? Well, big B, let's call big B this side, okay? Big B, the length of it, what would it be? Wouldn't it be the function value at x1? Little b, let's call it this, that would be the function value at x0. What about the height? Well, like we said, the height, kind of a misnomer here, that height would be the distance between the parallel sides. That's delta x, yes. So trapezoid 1 is f of x sub 1 plus f of x sub 0 delta x, and usually, let's write it. Should have written it in. Let's go f of x sub 0 plus f of x sub 1 times delta x. Well, I don't think it's too hard to imagine then. Trapezoid 2 would be a equals 1/2. Well, it's going to be the same thing, except the function values are with x1 and x2, right? So it's going to be 1/2 of f of x sub 1 plus f of x sub 2 times delta x. And then what about trapezoid 3? Well, same thing, except with x2 and x3, right? So the area is 1/2 f of x sub 2 plus f of x sub 3 delta x. So isn't the integral a to b f of x dx, isn't that going to be equal to the sum of all these three? So I'm going to add these three together. Now, without writing all that together, what are some things I can do? Well, here's what I can do. I can factor off a 1/2, so let's put that all out here, and then delta x out here, because all of them have delta x multiplied. So what do I have? I have f of x sub 0. Then I've got 2 f of x sub 1s. I've got 2 f of x sub 2s. And I've got 1 f of x sub 3. You okay with that? See where we get all that? So it's 1/2 f of x sub 0, 2 f of x sub 1, 2 f of x sub 2, f of x sub 3, and delta x. Sound okay so far? Well, let me just show you. If I use 4, trapezoid, the integral a to b f of x dx is going to be 1/2 f of x sub 0. Again, I'm going to have 2 f of x sub 1s, and then I'm going to have 2 f of x sub 2s, and then 2 f of x sub 3s, and then an f of x sub 4 delta x. Yeah, because if I use 4, look at it like this. Here's x sub 0. So I've got 1 f of x sub 0. Then f of x sub 1, well, it goes with, here's my trapezoids. The x sub 1, the f of x sub 1 goes with this trapezoid and that trapezoid, so I'm going to have 2 of it. This x sub 2, the f of x sub 2 goes with this trapezoid here, and it goes with that trapezoid there. And this trapezoid, these two here, have 2 f of x sub 3. So here's the point. No matter how many subintervals I want, 4, 3, 4, it's going to look very much something like this. And the pattern is, what's the pattern? I've got the first one, I've got 1 f of x a bit, right? The last one, I've got 1 of it. But what about the middle ones? They're always going to have 2 of them. That is the trapezoidal rule. Let me write that out. Does that make sense? See that? The middle ones are always going to be 2 times the function value at whatever value you're talking about. The middle ones always have 2, whereas the end ones is just 1. That's called the trapezoidal rule, and that's the way it works out. So here it is, kind of in general. Oh, and then the other thing is, they usually write these two parts together. Isn't that the same thing as delta x over 2? 1/2 delta x is delta x over 2. They usually write that as delta x over 2. So you've got delta x over 2 times 1, 2, 2, 2, 1. The middle ones are always doubled, if you will. So it goes like this. For n subintervals in your approximation, the trapezoidal rule works like this. The integral a to b f of x dx is approximately equal to delta x over 2. Like we said, that's always there. Then it's f of x sub 0 plus 2 f of x sub 1, 2 f of x sub 2, 2 f of x sub 3, until we get to where? Well, it goes out until 2, 2, 2 until I get to the last one, which is just f of x sub n. So all these middle ones are 2 times it. Okay? So that's a little bit different. Usually we're just adding the function values in here, but for the trapezoidal rule, we're doing 2 of the middle ones, and then up front here, we're also not just having delta x, we've got delta x divided by 2. So that's the difference between, say, the trapezoidal rule and the midpoint rule and all the others. Shall we do one? Let's do one. All right. So let's use the trapezoidal rule. I think I'm going to need all this space here, maybe. Let's see. Okay, use the trapezoidal rule with n equals 5. To approximate the integral 1 to 4 cosine x over x squared dx. See if we can do that. Trapezoidal rule. What would be first step? Everything hinges on delta x, doesn't it? All the x sub 1s, x sub 2s, and all that hinge on delta x. So delta x, b minus a over n. What's b and a and n? N is 5, obviously. Yeah, this is a and b, isn't it? A and b are just your endpoints. So it's 4 minus 1 over 5, so that's 3 over 5. Let's call that 0.6. I like to go ahead, too, and think about what the x sub n's are. X sub 0, of course, is a, where you start, so that's 1. And then x sub 1, how do I get x sub 1? Yeah, x sub 1, then we just go 0.6 over from that, so it would be 1.6. X sub 2 would be 0.6 plus that, 2.2. X sub 3 is 2.8. X sub 4, 3.4. And x sub 5, the last one is 4. And so then you have it all, and you don't have to necessarily write those out, but eventually you will. So here it is. By trapezoidal rule, the integral from 1 to 4 cosine of x over x squared, which, by the way, again, is 1. You can't evaluate that directly, even with all of our little tricks. Not going to be able to evaluate it. But by trapezoidal rule, we can say, yeah, that is approximately equal to delta x over 2. So that would be 0.6 divided by 2. That would be 0.3. Times then f of x sub 0, 1, plus, what's next? 2 times f of x sub 1, which is 1.6. And then it's 2 times f of 2.2. Then it's 2 times f of 2.8. I'm going to have to make smaller numbers here. I'm going to round around. F of 1, x sub 0, and then 2 times f of x sub 1. And then 2 times f of x sub 2, 2 times f of x sub 3, 2 times f of x sub 4, and then last but not least, just f of x sub 5, which is f. Yes. Which you can go through and evaluate all those if you want to, but we can use our vars and y vars. Remember that? Oh. Yeah, on your calculators there, the TIs anyway, vars, y vars. Go to vars. Oh, put this in for y1. Then go to your regular home screen there, and then go to vars. Oh, well, put in, we're going to use that, but put in 0.3, parentheses, and then we can just put these in. You know, this is going to be y1 of 1, but to get that y1 of 1, and you do this various different ways, but yeah, that's where you go to vars and then yvars, and then you can select your function. Then you do y1 of 1. Yeah, parentheses 1. Just like f of 1, except you're going to use y1 of 1. Then I'm going to do what? 2y1 1.6, and then 2y1 2.2, blah, blah, blah. See what you get. I think I know what you should get. Because I forgot my calculator, so I'll check you and see what it is. Then we got it? Negative 0.52252. Negative 0.52252. Yes. Should be what you get. Oh, you got 0.05. Yeah. Check it out.